Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone, and welcome back to the Future Leaders in Quantum pre-hackathon webinar series. As a reminder, the hackathon will take place starting May 16th and is open to everyone with 4 distinct tracks, including art, education, innovation, and science. There'll definitely be fun and inspiring projects for all backgrounds and skill levels. If you're enjoying these workshops and are looking for some more hands-on experience, please head to the AI for Good website or visit www.quantumcoalition.io to pre-register for the Flick Hackathon. Today's workshop is titled A Roadmap for Developing Inclusive Quantum Learning Resources. It's my pleasure to welcome our speaker, Associate Research Professor Dr. Emily Edwards from Duke University's Pratt School of Engineering. Professor Edwards is a recognized speaker in science communication, specializing in multimedia approaches that increase awareness, interest, and deep understanding of quantum information science and physics. And since 2011, she's co-created public resources like the Quantum Atlas and an immersive quantum computing game world designed for middle grade students. Today, she'll guide us through the art and science of building more inclusive, effective learning experiences in quantum technology and show us how we can all contribute to developing these important educational tools. Professor Edwards, thank you so much for being here, and over to you.
Thank you so much, Sean, and thank you for the invitation to speak today. Let me go ahead and just share my slides. Okay, yeah, so it's really exciting to be here, especially during the International Year of Quantum Science and Technology. A lot of the work I'm going to talk about is about the US and some of the efforts here that I've been involved in to support quantum education. But I hope that some of the activities that I'm talking about are of use, and I think maybe demonstrate that we're all in this together across the globe, trying to figure out how to bring quantum to everybody in a way that is inclusive and supports people wanting to go into this or even to just know more about quantum. My work is supported by the National Science Foundation in the US and the Laboratory for Physical Sciences, a lot of this work is done in partnership across many, many groups in academia, K-12, industry, professional societies. So I just wanted to flash this up here to say I'm the spokesperson, but this is not my work alone. In this talk, I want to, just level set and say a few words about what is quantum information, and for those who may not be as familiar with it, and a little bit about the motivation of why we're thinking about quantum education in the US and in the context of the science and engineering workforce and education system. I'm going to talk about some policies and approaches that have helped spur progress here in developing resources. And then I'm just going to touch on a few example learning resources and mention the gaps that I see both here and across the world that are opportunities for development. Hope that maybe some of you on this call will be interested in engaging in this and then thinking about how we could collaborate. Certainly, I do not know everything that is happening in quantum education resource building across the world. And so I look forward to hearing from you if you know of stuff that's happening so that I can have a better picture as well what's happening internationally. I will use the following acronyms in this talk that may or may not be familiar. So QISE, we use that to say quantum information, science, and engineering. And then I may say the word STEM a lot. And the word STEM here is the way in the US we say science, technology, engineering, and mathematics. You may use this in your own country as well. And so if you see STEM, it's not the stem of a plant, it's the stem of science education. When I think about quantum and when I talk to students and young people, particularly kids about it, the quantum and quantum information is really referring here for me to, as a place to start, for things that are really small. So thinking about atoms or subatomic sizes, or really cold, near absolute zero, or both. And there's a reason for this, because in order to do anything useful for technology in quantum, we both have to understand what's happening at the atomic or subatomic level, and we have to be able to control purely quantum features. So we need to get rid of all the heat that often makes quantum features disappear or make them difficult to control. So when you hear quantum, you're probably, especially quantum technology, the thing that the people are talking about is something very small or something very cold or both. It's more than just physics today. So while we have been celebrating 100 years since some physics theoretical discoveries and then followed with experimental discoveries, it is today really about controlling purely quantum features to improve technology, do science, solve problems, improve people's lives. In the 20th century, you may or may not know that quantum was there. And even though we don't see it directly, we can't see down to the atomic scale with our eyes, we can see the evidence for it. So MRI machines, magnetic resonant imaging, was developed, and it's useful and was developed because of our understanding of quantum mechanics. Similarly, the entire semiconductor and modern computing industry relies on our ability to understand how atoms come together in solids and interact with electrons to then manifest interesting effects in materials. We were also able to develop lasers, and lasers are awesome. And then later on in the 20th century, we were able to cool atoms using lasers, and we have developed very sophisticated atomic clocks, which are used in the global positioning system. In the 21st century, we want to do way more than we've already done. We want to go beyond understanding and leveraging our understanding of nature at small scales to build interesting technologies, but we want to control things like superposition entanglement to advance S&T. So this, if you hear about quantum, you're going to hear about things like quantum sensing, which could improve our ways of understanding geological and life sciences. Quantum computing, that's a very popular one right now, that companies around the world and governments around the world are investing in to try to race to build a full-scale quantum computer. And this type of computer has specific uses. It won't replace your regular computer on your desktop, or it won't replace supercomputers necessarily. It's a special purpose processor good for certain problems. We know there's applications for a full-scale quantum computer in encryption, and we know that there's also applications in understanding chemistry and physics and matter at atomic scales. Beyond that, we're not totally sure, but people think that there might be applications, and they're studying them in logistics, optimization, things like this. And then, of course, we can use another application of quantum in the 21st century is how we can use features of quantum mechanics to make information more secure as we send it over long distance. So we want to keep our information private and secure, which I think is a global challenge. So we, of course, are celebrating this, and the context of what I think about is the part of the UN resolution for the International Year of Quantum that talks about youth engagement and how it stresses that it's really important to develop pathways, to highlight the achievements of women, and to really focus on how we can bring more people into this field starting at a young age. And so this really resonates with me and what I've spent a lot of time over the last couple of years thinking about. the case in the US for starting early, I think maps well into the rest of the globe. But in general, we want to take students and youth when they're very young and they're like natural scientists and natural engineers, they're explorers. And we want to expose them to quantum to increase their interest in this area or other science and engineering pathways. And it's important to start early because students often start to feel like they don't belong in this field as they get older and build their identities. And so if you start early and familiarize it, then it will become more likely that students might feel like they could belong and contribute and make decisions about this field and this technology as it continues to impact the world in the 21st century. Also, we need to increase public awareness about this, and this starts early. We want to address all ages, but you have to really focus on youth if you want to see a change in public awareness over the long haul. And of course, there's a shortage globally in both access and people entering into these pathways. And so there's lots of reasons that we want to start early and particularly make sure opportunities are available to everybody. This is a challenge, of course. I like to acknowledge in every one of my talks that quantum sounds like it's only for geniuses. It sounds spooky, it sounds mystical. And I know this is not just in the US because I've heard many of my international colleagues say that their goal is to demystify this area. So for whatever reason, quantum has an aura of scariness about it that really, I think, that the combination, we can't see it directly. We can see evidence for it, but we can't see it directly. And then also on top of that, we don't teach it in many schools around the world. I think this creates a big barrier to this area. And so, and a lot of confusion. So I think it's important, and it's not totally impossible. In the US, a lot of the work is starting early is also motivated by some of our workforce characteristics. So just very quickly, the US STEM workforce is a pretty small component of our workforce. And this is a very complicated diagram. So I apologize for it. It's from one of our sort of the Census Bureau that kind of tracks characteristics in the US. But essentially, what's important to note is that the S&E occupations here, the 9422, which is 9,422,000, because you have to, these are in scaled units, is a very small percentage of the US, and that most people do not have a bachelor's degree in the US over the age of 25, and most people are in about half of the science-related workforce doesn't have a bachelor's degree. And so it's even more important when you have this kind of demographics of our workforce and these characteristics that we have to start early if we want to engage everybody in this, because many students will not necessarily go to college. And so while those and be exposed to this, and even if they do go to college, they may not see the word quantum until an advanced course. And so this is just this laid out by our states. So in the US, we have like different regions called states, and so we have the demographics vary across our 50 states. And so this again is just a piece of this that says the US S&E occupation. So people who are directly not just the related fields, but directly consider themselves science engineers. The occupations for this are quite a small percentage of our workforce. And the bachelor's degree holders are less than half in most states in the US. And so, I'm not saying everybody needs to go into quantum, but I'm saying if we want to think about how we bring people into this, we really have to think about the youth component. And that's pretty clear from these graphs. And moreover, because, it's important, like the UN resolution lays out, that we should be also focusing particularly on women. I want to acknowledge that the areas of science that directly contribute to quantum show a significant lack of women participation in all degrees, bachelor's, master's, and the highest level doctorate. And particularly, I will say in the US, we have a historic historic underrepresented issue with African Americans, and there have only been 220 PhDs in physics awarded to have African American women, according to the AWIP, ever. So, so we have a long way to go. So I won't hammer this point home because I want to get to the next parts, but I'll be happy to share these slides with the organizers to make them available. But I just want to say that, yeah, computer science, it's the same. And we actually were making progress with women representation and have gone down over the years. So there's a lot of work here and it starts early. And that's the main point. So given that, there are policies in place in the US to try to support this. The National Quantum Initiative Act is our version of federal policy that tries to accelerate investment and advancement in quantum information science applications. It was passed in 2018, and it's up right now they're reworking it in Congress currently, actually. The first version of this did articulate the need for a workforce pipeline, but it then articulated curriculum, but starting at the undergraduate level. But our laws like this are very, they're a little malleable and can change over time. And so in response to the efforts of I would say, people working on pre-college education across government academia, that group that I said before that I co-lead, I was happy to see that the NQI Act, the National Quantum Initiative, was amended to include ages before college. So we call it elementary, middle, and high school here. And so that's referring to people who are ages 5 through 18. And so this continues to expand as an area of interest in this country, but it's very slow. But my point in showing this is that you need policies to make this happen. So while in our country, our educational system is highly local to all those states I was showing. So you can, let's see, you can see these here. These are how our regions are broken up. It's highly local. But usually we like to have a federal strategy, so a national strategy on certain areas of education to guide investments, particularly in science, to help support the implementation locally. And so it's a complicated system with 50 different 50 different regions deciding how to implement, but you still need this national strategy. And so this is something that I've been involved in. I don't work for our government. I work for an academic institution, but I've been very involved in this area of sort of national strategy across the different parts of the ecosystem. And so, as I said, so we've got national strategy, we've got state level, and I think this is similar in many countries where there's different levels of policy and decision makers that have to work. And so that's the reason I show this, is that it's an all hands on deck or everybody together approach to getting policies that then can drive opportunities for youth. And so in this country, we have to have standards. And so this is happening now. All of this takes, so we've been working on this for five years, early education in the quantum education formally for 5 years. And we've made some headway, and there are lots of programs out there, but it requires long-term investment. And so one of the things I like to show is again, how we can scale. And so I was involved in writing a paper to determine what's kind of next steps. And I think some of the things here are gaps that also are globally, not just specific to the US. So this is published in an international journal so that folks can see what is needed to move quantum education opportunity forward and resource development forward in an inclusive way. And so this paper outlines several areas and calls for a national quantum education center to help sustain long-term investment. And I think this model could work in many areas around the globe so that there is a place for people to keep convening around, since it takes so long and education is not a for-profit industry. Industry is not going to step in. Companies are not going to step in and fund this by themselves. Governments are not going to step in and do this alone. Academics are not going to step in, and certainly not teachers who are trying to teach during the school day are not going to, everybody has to work together. So you need a hub, a center to pull it together. So I refer you to this paper.
Professor Edwards, I just had a quick question about the
Sure.
kinds of policies that you outlined previously. I was wondering, do policies like those that are emerging for quantum science, the ones that you've been working on, do they have parallels in other areas, other perhaps science areas or areas of focus that have seen this kind of special policy support?
Yes, it's a great question. So, the most recent policy changes we're seeing in education that are kind of similar or have happened in recent decades are in computer science education in the US, and also more recently AI education, which is tightly tied to that. Computer science, there are computer science organizations who have successfully advocated for policy changes across many different levels, that federal or national, regional, hyperlocal, city, town, those places. Different computer science organizations started that effort about 25 years ago. And they've made significant progress. So computer science education is now more available to students across the US than it ever was. They have both formal and informal. And in an effort to not reinvent the wheel, I've spoken to a lot of those people who were at the beginning or are now working on that to try to model our quantum education efforts after that. So it's a lesson that learned from the others in the community. Now, they had pitfalls, and some of the things are going to be different. A good example of what's different in quantum education is we're not seeking to have standalone quantum education courses at high school, elementary, or middle. So for students who are ages 5 to 18, we don't need standalone courses in every school. There should be those available for students, but they don't need to be in every school, in my opinion. And that is the opinion of most of the people working on this, that we need to connect to current curricula and find out what are the shared foundational ideas and concepts that quantum shares with other areas, computer science, physics, mathematics, and I'm going to talk about that in a minute. And what are those shared things, and where can quantum be infused, and where can quantum lift up science education? So that's been our approach, but we are definitely looking at the computer science successes and seeing where we can model after. And then AI is happening kind of at the same time. And I would say AI education, a lot of the stuff that's happening with AI education is still we still don't understand because it's only really recently become readily available to the public. And so I would say it's important to proceed with caution when doing educational policy, because you really need to do it based on evidence and research successes so that you don't introduce something, particularly a new modality that students use and have access to without knowing how it's going to impact them. And so that's why I like to see the AI for good, because I think it's very important. Thank you for that question. So in a nutshell, that's kind of a summary of where the policies have been in the US, and I went through it rather quickly. But the main thing is it's long term, and we really have to work with educators because they are really the experts about how to work with their students and work locally. And we are trying to figure out these connections. So at present, there's a lot of resources that have come out in the last several years. Some of them are informal, which are like the anytime, if you want to introduce quantum in your classroom or at your home, do some activity on the weekend. Those are what we call informal, if they're done kind of ad hoc and are not tied to curriculum. There is kind of an overlap area between formal and informal. Informal is like the process of curriculum development with assessments and full integration, where teachers are really both receiving professional development on something and then able to teach it to their students in a confident and accurate way. This kind of thing takes years and is really just developing. We're a ways off from this. And so there are areas that tie to curriculum and activities and resources where teachers can connect in, but it's not, of course, mandatory because there aren't state standards that are driving it. So I want to share a couple of informal and formal resources and ideas out there, and then I will talk about the gaps. So the Q12 partnership that I showed at the beginning with all the logos and everything, we, in talking to actually code.org, we modeled a program after their hour of code, which is their kind of informal way of getting into getting teachers something now to have for their students. And so we convened a lot of people to ask what was needed in the beginning 5 years ago. And many people, both here and overseas, said that they needed some fun, informal activities right now. So we launched a program called Quantime, which is really a way to curate and share resources from the community. I did not create all the resources that are out there, but we have provided guidance to organizations that say, hey, if you have something for young people that you want to share, try, write a guide for how to use it, write all the materials down, sort of write these facilitation guides, how much time it would take, does it cost anything, and we'll put it on our website, and then we'll share it with teachers across the US. And this is, they're publicly available internationally. We've had many people internationally sign up and say they want to use this, and it's open to everybody. And so our main goal is to just help people, help teachers access the activities that are out there in the community, and then help the larger curriculum development, resource development community see where the gaps are and not recreate things over and over. And so I'll say a few words about that. We've run this a few years in a row and reached over 500 teachers. I think as of this year, it's actually probably over 1,000 teachers across dozens of states, which when you reach a teacher, you're reaching hundreds of children. So, and we've had, the numbers haven't been updated. These are about a year old, but tens of thousands of participants online and doing hands-on activities. One of the examples from this, and this is actually one that I did develop, full disclosure, through another program, but it is one that has both offline and online components, which is why I wanted to share it. So one area of popular resource development in the quantum community and the education community has been games. I feel like every week I learn, particularly from abroad, from outside the US, of games that are coming about. And so this is a really exciting area because young people get excited when they play. And I love play because I think we don't play enough at all ages. So this game, led by University of Chicago, I'm a collaborator on this project, is developing an online quantum computing game where students learn through game mechanics. It has characters, they play mini games, and it's not heavy-handed because it is a game. It's supposed to be fun. And then we connect quantum concepts to it through a rewards center. Anybody can access this game. There is a research option, and then there's also a public option where you don't have to share your data. We've developed or are developing currently an offline option, but it is available that you can print out on stickers and kind of play, but you can't order the decks yet. But a game that is an offline option for people to engage with this world and learn quantum concepts, and that's called Collapsing Qubits. What I want to highlight here, though, is that there are ways to become familiar with quantum concepts through play. And I think the community is doing a really good job engaging in that. And I think this is a wide open space for development because a lot of what's been done has focused on quantum computing. But there's certainly games that people can make based on quantum, or that teach quantum sensing and quantum communication. The other area of informal development that I think is a real opportunity and so critical, and really alluded to in the UN resolution, is the idea of role models. So there's a lot of research to support the idea that people need role models. I mean, it seems a little bit obvious. We don't just, we maybe start off as curious explorers as young people, but then sometimes barriers come up, or sometimes we don't know the next step. And so having mentors and role models to help guide us and motivate us is so important. And this is particularly important for young people around ages 10 to 14, where they're really building their identity and where they fit in the scientific and technological world that they're growing up in. And so we've developed a few resources, like a video with an astronaut and like um, LeVar Burton, who's kind of a pop culture icon in the US. So we've developed some videos out there, but like this is a wide open space. And I want to say that, you know, I want to acknowledge some of the role models. I take this opportunity to acknowledge some of the role models that have been in my life, because I think it's important for us, even as adults, to remember that we need role models and mentors, even at this age. So I'm 45, and I will say that so one of the more recent role models in my life has been Professor Karen Jo Matzler from Texas. She is a amazing master teacher and education researcher, and she has spent the better part of her life providing professional development for physics teachers. And this is what she does all the time. She's developed some of the resources that are available on our website, and she has provided thousands of teachers educational opportunities. And so she's one of my heroes, and really I've learned so much for how we need to do quantum education in this country from her. And one of the teachers she taught is Professor Majida Murdoch from Morgan State University, who's also a teacher in Baltimore, Maryland. And she's taught thousands of students and now works with teachers in Maryland about quantum. And so I think it's really important to see the network effect of having these kind of connections and role models. And so I'm gonna just indulge a little bit and say a few more scientist role models in honor of International Year. So, you know, there are women everywhere in science and always have been. And some of them are more hidden. And so I'll say that this woman on the right in the color photo, her name was Catherine Gebbie, and she was a, a, a scientist at a national lab here in the US, National Institute of Standards and Technology, which is a lab that has a long history of quantum research. And under her leadership, when she was directing one of the labs, under her leadership, 4 Nobel Prizes were awarded to scientists working in that lab related to topics on quantum, particularly atomic physics topics. And she believed in a national lab setting that scientists can do the work that is needed and not just and be able to be explorers. And so I so appreciated her. I met her. I was, as I grew older, I was friends with her, and I would ask her about her career, and she would just tell me about her role model, which was her aunt, Catherine Burr Blodgett, the first woman to earn a PhD in physics from Cambridge University, and the first woman scientist to work at General Electric. And this Catherine Burr Blodgett worked as a chemist with, even though she was a physicist, she worked as a chemist and developed the thin films that are the precursor to the anti-reflective coatings on glasses, which are really important for eyesight. She also worked to invent techniques to keep airplanes safe by de-icing with films. So she was amazing. She was called the Invisible Woman, even though she won many accolades. She was called the Invisible Woman because her technique was used to make glass invisible. So it's referring to her invention and what she did. So I wanted to digress a little bit to say we need more of these stories. We should, so as you think about developing resources, I encourage you to think broadly that there are the educational resources about the science, but then there are the educational resources about the people in your countries, the leaders, the scientists at all ages, the people that are emerging, because I think students need to see the person the next stage up, but they also need to see the person 3 stages away in their career to be able to be motivated in these areas that are emerging and perhaps unfamiliar. So this is another opportunity for the development of resources. Sean, should I pause here if there are any questions, or I can keep going? Because I'm going to switch to formal education now.
I mean, I think maybe a good question is, who's your hero when you think about science? Is it Catherine, or are there other figures who have helped you in your journey in science?
Okay, I will just tell you that my hero in general may not be in science. It is my sister. So my sister, my older sister, uh, is an amazing mother and advocate for education. And so I would say on the education policy side, my eldest sibling is my hero. I would say my hero in science, there are so many to choose from. So I've just chosen three today. Let me think about it as we go on and see if there anybody else I want to give a shout out to. It's a great question. um, Okay, so I borrowed a quote from this paper. So there is a lot of work in Europe on quantum education that I want to acknowledge that has really paved the way for success in many areas and many countries. So I think they're pretty far along in quantum education in the formal space. And again, when I say formal, I know there are blurry boundaries, but I'm referring to stuff that is happening in the classroom that is really well developed. With assessments and integrated with their curricula. And I love this quote because I think it captures everything that modern upper secondary school physics curricula would be incomplete without some basic quantum physics concepts. And I would argue and take it a step further that modern upper science curricula is incomplete, and possibly even earlier, because I think we're seeing more and more with research that students can conceptualize the foundational concepts in quantum quite early. Probability, the quantum states, the idea of measurement and uncertainty. These are all foundational ideas that if students conceptualize early and get a grasp on, they will have an easier time in quantum. So there was a study by that same group that sort of went through publicly available curricular documents and articulated where quantum falls in and what are the topics that are being covered in these European curriculums. And so there are areas that are not so unfamiliar, and actually some of which appear in the chemistry curricula in the US. But they go a step further. They cover not just probability, but they cover ideas of uncertainty principle, philosophical interpretations. A lot of groups talk about interactions with light and matter, which is an area of opportunity, I think, to be developed, and so on. In the US, we have standards currently that I've tracked in Texas, Virginia, and there are some in Ohio. And there are lots of connections of these topics, some of these topics to existing science areas. I will say, and you can see it from here, entanglement, which is one of the, if not the right key feature of quantum mechanics, and the one that you must have in many applications that are in the 21st century to get a benefit. In the 20th century, there's not as much control or utilization of entanglement, but in the 21st century, that's the purely quantum feature people are trying to control to do something more profound and more impactful and more novel in the areas of quantum communication, quantum sensing, and quantum computing. And you'll note that that is one that is not widespread and taught. And that's a major gap. So we looked at this and decided to develop a framework for how quantum information science and engineering could be taught and coupled and infused into current science curriculum. And so we asked these questions of that every emergent technology, and AI education should be doing the same thing. Other areas should be doing the same thing as they emerge. What are the key concepts that we think students should know about this topic upon graduation? Do any of them match standards or curricula that already exist? And if so, how? What are some example ways? We call it learning trajectories. So this way that students could build upon the concepts. And what are the examples that might be out there of good quantum curricula and lessons? And so we started this project a while ago. There are lots, these lists at the bottom are projects that are developing lessons and curricula currently in the last couple of years and researching them. And so what we found is that There are opportunities for putting quantum lessons and resources in chemistry, particularly around atomic structure, energy, photons, superposition. Students are already learning some of this stuff, but they're not hearing the word quantum attached to it. There's a different vocabulary, perhaps, in introductory chemistry. In math, students learn about probability and vectors, but they're not, again, hearing applications. So there's an opportunity there. In physics in the US, students learn about the electromagnetic spectrum and waves, but they don't actually learn about the quantum properties of light or light matter interaction as standard. And so there's an opportunity for extension. And in computer science, I think it's going to be hard to get quantum computing in there, but if so, there are, it would be through quantum computing modules where you're trying to do similar programming, I think, and comparing quantum computing platforms versus classical computing, so bits versus quantum bits. So we worked on this. It's publicly available. And you can see that because most students in the US take chemistry, that is an open area of opportunity that needs to be explored and would be the fastest way to scale quantum literacy at these age groups.
Professor
I don't,
Edwards,
yeah,
sorry.
go ahead.
I just wanted to ask a really quick question about, maybe one concern I can imagine educators might have is being able to fit all these ideas in within their kind of the existing time and resource constraints that they have already in this in maybe a high school setting. And so how do you think the best way we respond to kind of those challenges or perhaps those concerns from people who are trying to communicate as much as possible to seniors, for example?
Yeah, it's really it's a great question. So a lot of times these extra topics, I would say the easiest way these extra topics get into schools is like the week before the winter holidays and the week before the summer holidays. There's sometimes extra time after the exams to add extra topics. I would say the more robust way to do it would be to modify the modules on chemistry or physics to add more context and connections to applications and like quantum vocabulary. That's going to take a little more time, because you can imagine that when a teacher teaches about energy, discrete energy levels and the structure of an atom, there is probably time there to go into depth and say, well, guess what? This idea of absorption, emission, electronic transitions is used for some types of quantum computing platforms. It's used to store information. So I think a lot of it is this the second easiest way is in through this vocabulary change to expose students during the lesson itself. So those are the two ways. In the long term, I think there needs to be a readjustment of how we prioritize. So teachers have a lot on their plate. There's all these things they've got to do. And schools and districts make decisions about what needs to be prioritized. They're like, prioritize this thing, prioritize this thing. There's no way teachers get to everything as it is. And so I do think there needs to be a shifting of what are the foundational ideas that are being prioritized for teachers and educators, particularly at the K through 8 level. What are those science ideas that are being taught? What is being prioritized? How are those ideas feeding into a student's understanding of more advanced areas like quantum? Yeah. Okay, so we're coming to a little bit of time here, so I just want to make sure. So I wanted to give an example resource that there's actually two that are very popular, I think, and kind of doable. With very low cost materials. And so one of them is the Measuring the Width of a Human Hair. This is from a Canadian institution, the University of Waterloo, the Institute of Quantum Computing. This is available. They've allowed us to make it available through our website because, again, we're just trying to have like a resource repository for people of vetted material. And this goes over superposition, quantum sensing, and uncertainty, and gives more defined learning goals that make it more in this mostly formal space. There isn't an assessment, but there's a student guide, there are student questions, there's engagement. So this is an activity that could be done And it would match some of the stuff that's going on in Europe, where they may have already decided to make time for it in their day, or maybe there's stuff, in the country you're in where you've already decided to make time in your day, and here's an activity. Another one that's very popular is glow in the dark stuff. Now, I thought this one was going to be only popular with little kids. This is popular with everybody, including our teachers. And this is the one I was just talking about electronic transitions and articulating those connections of the fundamental science to the application space. And this is also available. And this was developed by the University of Wisconsin in the US. So I put this slide up. I'm not going to go over everything because there are lots of resources out there. I don't know all of them, although my project this summer with one of our wonderful staff members at U Chicago, my collaborator, we are going to add all the resources we're learning about that aren't available on our website and flesh that out and make deeper connections. And so if you have something, send it along. There's a lot out here, and a lot of these are developed by companies. Some of them are developed by folks outside of the US. So please, if you have more, bring it. If you don't, here's a good place to start. Sean, you kindly mentioned the Quantum Atlas at the beginning. The Quantum Atlas is a glossary. So if you know nothing about quantum, places like the Quantum Atlas, I do think offer. QPlay Learn is another one, and Quantum Made Simple. Those are ones that really offer you like a first step into quantum that are more glossary and definition focused, I would say. Okay, I promised to say gaps in this talk. So what I'm seeing currently today are that, okay, a lot of what's been developed is not multilingual. So one of the ways we can make this more inclusive and reach lots of people around the world are to take what's out there, whoever develops it, and translate it into some different languages. And this is going to take work because science translation is not so robust, even when it's automated. And so it requires somebody who speaks the target language natively to check anything that's been automatically translated. And so, but this is like a lift that can be done and is not, I don't think, terribly hard to take all of the resources that people know about that are written in form and take them and translate them into some more languages. This would increase impact significantly. Topically, if you're a curricular developer or a researcher wanting to get into making resources, then I will say in looking at this that there's hardly anything in chemistry, math, other than that electronic transitions one, which is really physics focused. Chemistry, math, quantum sensing, quantum network, entanglement. There's not a lot out there in these domains. And in fact, there's tons of duplication in the quantum education resource development space. People always jump to polarization, which is excellent and can be used in many ways. It's a great way to explain several quantum concepts. And wave-particle duality, because physicists love wave-particle duality. They love to talk about wave-particle duality. It's like their go-to when they want to introduce quantum. But the truth is that while those are really excellent, it's not always going to be the way that most people get into this. And so by picking a diversity of activities, then we increase pathways into this. Not most students, I think, are not going to go wave particle duality. Yes, I want a career in quantum. And so I think that's a big jump. And that's asking a heavy lift of wave particle duality. So I think look at the opportunities and let's move away from duplication. That's my ask. And then there's a lot of development in games and particularly quantum computing. And so what I would say is if you're developing games and you have an awesome idea, go for it. If you are like, I want to develop a game, but I don't know what topic to cover, I would encourage you to consider a creative game around quantum sensing, quantum communication, entanglement, these topics that are really missing things. And lastly, I want to just say that improving science education requires so much dialogue and collaboration. I look forward to learning from people attending this webinar and people throughout the coming years. I've already learned a lot, as I mentioned, at least one education mentor that I really look to for guidance in this space. And so this is not done alone at all. It's a collaboration. And so I like to leave this slide up to say, here are lots of ways I think people can contribute and that I'm seeing people contribute. I'm sure I'm missing something on here, but the message of this slide is partner, work together, and work at all levels and figure out where to invest. And in particularly in this time, I can't say it enough, that we need to incentivize professionals to do this work because it can't be done alone by teachers. And the incentive systems in academia and research and industry are not set up to support science education or inclusive science education globally. So this really requires us to not wait for it to happen and not wait for communities to just suddenly grow grassroots efforts. You really have to have reinforce priorities and put money to it and have incentives for everybody at all education levels and sectors to participate. Thank you so much.
Thank you so much for the wonderful talk. I think I have maybe two questions to kind of finish up on. The first is, in your view and kind of your understanding of the international education space, do you think there are any quite successful national models of quantum education that you see as kind of good places to borrow some of the best practices from?
Right. So I do not necessarily think there's a place that's doing this, at least from from publicly available information, that's sort of doing this like sort of the holistic best way. But I will say, the countries in Europe that have been able to deploy curricula that are increasing, that have quantum concepts in them, though I would look to those countries. And in particularly, I think some of the efforts in Europe, their flagship has made this the EU flagship project has made this a priority. And they've, I think, put a lot of effort to figuring out how to really put investments where they need to go to develop resources that follow their existing curriculum. So I would look there. And then I think also the informally speaking, I'd be remiss if I didn't mention that the World Quantum Day effort that is sort of set the stage in some ways for awareness that made International Year so successful so far is the World Quantum Day effort. This was a grassroots movement to do that is really about informal education. So it's not so much a center to drive formal education forward. There, you really do need to look to things like the flagship and how they're deploying it across different countries. Like for instance, Switzerland has like a technician program, and they have investments in some other areas of informal education. That kind of stuff really does happen locally, and there's not one model that will work for everybody because it's so different. But from a public outreach perspective, I do think World Quantum Day has done a good job.
Great. And I think maybe my last question is, I noticed that you mentioned that quantum network and communication needs a bit more action behind it. So if you could give the ITU and the kind of broader global community some homework coming out of this webinar, what would it be? So like for example, specific steps to kind of accelerate quantum education in quantum communications and networking in their own communities, for example.
Right. So first, I would say a call to action is for people to creatively develop resources in quantum communication that go beyond QKD, which is the one that people like to use particularly out there. But I will say the way to accelerate this in their own communities truly is, I think, to find advocates locally that are interested in this and see if people can learn about this using the resources available and then develop their own. I mean, it's unfortunate because it requires that kind of local action. What I will say is if you do not have somebody locally, if you're in a place that there's like just not a lot of quantum stuff happening, which we know this is true for a lot of places around the world, what I think International Year provides is a way to connect into that network. So I would be happy if anybody wanted to reach out and connect. I'm on the steering committee. There's a broad network both through World Quantum Day and the International Year that can help places, particularly in the global South, where there just aren't a lot of quantum activities. And then I think, honestly, Sean, the answer has to be tailored to the region. So for my call to action, though, generally speaking, where it would be focus on making resources. If you have the ability to create and be a creator of education and curriculum in this space, then look to those gaps and work on them. And please connect with me and others in quantum education, because I think there are people who'd be happy to help. Like Canada has a large QKD education effort and quantum communication effort, and I think they'd be certainly happy to connect with people who are interested in it.
Great. Well, Professor Edwards, thank you so much for your fantastic talk. And to our audience, we look forward to seeing you again soon with our next workshops. And please check out our website for more updates and register for the Future Leaders in Quantum Hackathon this May. And we hope to see you all there.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.